Okay, so this time we're doing list coloring. I kind of introduced this last time, but let me just kind of briefly remind you what it is. So basically the idea is, so each vertex in a graph, so G is a graph, has a list LV of colors. And our goal is to find a proper coloring where each vertex gets a color in its own list, right? And different vertices may have different lists. So find a coloring. So proper coloring f of G such that f of V is in the list for V for all vertices V. Okay, and then this kind of concept, oh yeah, so I'll call this an L coloring. So we say F is an L coloring. Meaning like L is some specific function that maps the vertices to sets of colors, and like for this choice of L, F is an L coloring. Okay, and then there's this list chromatic number, which is the minimum K such that so G has an L coloring for every list assignment. So list assignment, I just mean an assignment like this L, this assignment of lists to the vertices. So for every list assignment L such that the size of LV is at least K for all vertices. Okay. So it's kind of like the chromatic number, but like the chromatic number, every vertex has to get a color, let's say between 1 and K, or from some specific list of K colors. Now the difference is like, okay, every vertex has K available colors, but different vertices might have different colors available, right? So is the concept clear? Okay, and this is the list chromatic number. So then there's also like an edge version of this. And okay, so then you assign lists to the edges and you want to get a proper coloring. To kind of explain this in a faster way, I can just say like the list chromatic number the list chromatic index, so chi L prime of G, is just like the list chromatic number of the line graph of G. So yeah, instead you assign lists to the edges. Okay. And this is like the list chromatic index. So basically you use the word number when you're coloring vertices and index when you're coloring edges. So okay, so let's recall from last time. We had this theorem. Oh, actually, maybe before I do anything, let's kind of observe a kind of easy relationship between these list chromatic numbers and indexes and the usual chromatic number. So So if I have a graph G, can anyone tell me like kind of a relationship between this list chromatic number and index? Like one should be at least the other or something. So which one do you think is, sorry? Yeah. So how would you like argue that? Yeah, we did an example last class where it's like strictly larger. So that's, okay, so then therefore the inequality can't go the other way, that's for sure. But I guess how would I prove that this is always at least that one? That's the idea, right? So if I give the list, like let's say the numbers 1 up to k to every vertex, then like the graph has a proper k coloring if and only if it has a list coloring for that set of lists. So yeah, so it's true because yeah, so if L of v is just 1 up to k, let's say, then you know G has an L coloring if and only if the chromatic number of G is at most k. So yeah, like, anyway, so if I gave everyone a list of 1 up to the chromatic number -1, then there would be no coloring. And so, yeah, so that proves this bound. And generally, this thing can, like the gap can be really, really large. So I gave an example last time of like a graph with chromatic number 2 and list chromatic number 3. You could also have a graph of chromatic number 2 and list chromatic number 1,000,000. So I think that's actually going to come up on one of the assignments. So yeah, the gap can be very large. Okay, and obviously if this is true, then obviously like the same is true for the index thing because it's just the same, except we're coloring edges. Okay, last time we quickly kind of explained a proof of Koenig's edge coloring theorem. Which said that for every graph G, the chromatic index, without lists, just the usual thing. Oh, so for every bipartite graph, I mean. So the chromatic index equals delta of G for every bipartite G. Okay. So and this is like not too hard. And so let's prove something which is like a bit more profound and actually quite surprising, which is the theorem of Galvin, which says the same thing holds for the list chromatic index. So the list chromatic index of G is equal to delta of G for every bipartite graph. So yeah, no matter how you assign lists to the edges of the graph, if you've got at least delta colors in every list, you can find a coloring. And actually, this is related to a famous conjecture called the, so it's an open conjecture called the list coloring conjecture. Which says that for every graph, it says that the list chromatic index of G should equal the chromatic index of G for every graph G. So not just bipartite graphs, but every graph. And this is like, so it's a conjecture, so we don't know if it's true or false. So that's, but this theorem says it's true if it's bipartite, right? Because then list chromatic index equals delta, and so does the chromatic index. So it's true for bipartite graphs. But nobody knows if this is true in general. Okay. Any questions about this so far, statement and stuff?
Are there any examples satisfy this condition?
I mean, I guess any graph that has been checked has, because otherwise we'd have a counterexample. But I think the most, probably the most famous result where we know a big class of graphs that satisfies this conjecture is this one. It's known that this is kind of asymptotically true, that if you have like the list chromatic index is at most, let's say, 1 plus epsilon times delta, if delta is sufficiently large. So like this is kind of known asymptotically, but in terms of exact results, I don't know very much more apart from this one. And of course, if you do some small cases, then you can probably prove exact results, but yeah. I don't know if that answers the question or not, but any other questions about this? Okay, so what we're going to prove is this Galvin's theorem. Okay. So, I mean, sometimes I'm going to sort of go back and forth. Like we're trying to color the edges of the graph G. G is a bipartite graph, which is the same as coloring the vertices of the line graph. And so sometimes it's going to be useful to go back and forth. Right, so I'm gonna now state a lemma that we're going to use on the line graph of G. Okay, but first I actually need some definitions. So a kernel of a digraph D is a set of vertices. So it's a set K of vertices of D with two properties, so such that, so first of all, K is a stable set, so it has no arcs inside of it. And any vertex that's outside of K, so it's in the vertex set of D, take away K, has an out neighbor in K. Yeah, the idea is like, this is my digraph. My kernel, if this is a kernel K, there are no arcs inside of K, but everything outside will send some arc coming into K. So everything outside should have an out neighbor in K, but there are no arcs inside of K, right? This doesn't always exist. Like, for example, if I took like a triangle and put like a cyclic kind of orientation on it, well, kind of good luck trying to find a kernel in this thing, because the only independent sets are of size 1. So you could just take one vertex, but that one doesn't have an arc going in. So these don't always have kernel. Digraphs don't always have kernels, but it's useful if they do. And moreover, it's useful to have the following properties. So I'll say that a digraph is kernel perfect okay. So if every induced subdigraph has a kernel. Okay. So induced subdigraph, it's kind of like an induced subgraph, right? So like induced subdigraph is I pick some vertices and I look at, you have to keep all of the arcs inside of it. And then, yeah, you want every induced subdigraph to have a kernel. Okay, so what's the relevance of this? So it's the following lemma, so just to keep in mind, like our kind of main goal here is to prove this theorem. So this lemma I'm going to apply to the line graph of G. So this is a lemma which we will apply to the line graph, but I'll just state it kind of for any graph. By the way, I'm not writing L of G because I think that's going to be confusing because L of V is the list for V, and now L of G, like this is usually the line graph, and there's going to be too many capital L's. So I'll just keep saying line graph. Okay, so let H be a graph, which is going to be the line graph of G later. And suppose that D is like a digraph, well, a kernel perfect digraph obtained by orienting the edges of H. Okay, so I just mean somehow we've chosen directions for the edges of H to make a kernel perfect digraph. So if L is a list assignment for H, such that the list of every vertex is at least the out degree. So I'll write that as like deg, deg for degree plus for like the out degree, so the number of edges pointing out of the vertex, plus 1 for all vertices of H. Then H has an L coloring. A little bit of a technical lemma, but yeah, so basically, we want to apply this, by the way, to the line graph. So what we're going to do like later is take a bipartite graph, take the line graph, and just try to find a kernel perfect orientation of it where the out degrees are not too large. Right? Because if we can keep these numbers, all of these out degrees small, and find a kernel perfect orientation, then we're going to be happy. So that's how we're going to apply this. Okay. So the proof is going to be by induction on the number of vertices of the graph H. Okay, if there's like one vertex, it's easy, so let's forget about the basis case, right? So, yeah. So I'll just say if the number of vertices is 1, tick mark, right? That just means that you have a unique vertex and like it has at least one color, so just give it that color. Okay. So this proof is like almost as short as the whole statement of the theorem. It's actually really kind of nice. So let C be any color. And what do I mean by color now? Well, a color is like an element of the union of all the lists, right? Okay. So this color, like some vertices have that color in their list and some don't, right? Some vertices could use the color C and some can't, right? Let's look at all the vertices that have C in their list. So let's say A be the set of all vertices of H such that the color C appears in the list of V. Okay. So one thing I know is that if I'm going to use this color C, I need to use it on a stable set of vertices, right? Like it has to be a proper coloring. So, and of course the vertices I use the color C on, they have to be in this set A, right? So I want to find a stable set in A and basically give those vertices color C, delete them, and just hope that I can use induction. Can anyone see like maybe what I might want to do? Like how would I identify a stable set in A that I should give the color C to? So I need to somehow use the assumptions of the lemma. Any thoughts? It's kind of a lot of information here, but I'm going to use this kernel perfect thing, right? So since the digraph D is kernel perfect, so we can let K be a kernel in the digraph D, like the subdigraph of D induced by A. So being a kernel means it's a stable set. And the fact that it's like in this set A, like all the vertices of K are allowed to get this color C because K is a subset of A. So what I'm going to do is like basically color the vertices of K with C. So this is kind of my basically like a sort of procedure. Delete C from all of the lists. So like after I give the color C to vertices in K, I might not be able to use the color C on other vertices because they might be adjacent to things in K. So I'm going to delete the color C from the lists of all vertices that are not in K. But the thing is, yeah. Okay, and now I want to see that the inductive, that I'm done by induction. Oh, so after I color these vertices with C, I also delete them from the graph. Okay, so this is going to give me a smaller graph once I've colored them with C and deleted them. And yeah, I want to say that the inductive, that the conditions still hold. Um, so here's why the conditions hold, right? Because, okay, any vertex that's in A that I didn't delete, like it used to have C in its list, and now it's lost C from its list. But also, each of those vertices in A had a neighbor in K, an out neighbor. So any vertex in A lost one element from its list, but it also lost at least one out neighbor. So this went down by 1, and that went down by 1, but the inequality still holds. Any vertex that's not in A didn't have C in its list anyway, so its list stayed the same, and maybe its out degree went down or whatever, it doesn't matter. Like this stayed the same, so this inequality is still going to hold for those vertices. And also, like after I delete a set of vertices, I delete K, it's still kernel perfect because every induced subgraph of H had a kernel, so every induced subgraph of H minus K also has a kernel. So yeah. So yeah, there's not really space here to write this, but basically apply induction. Okay, and the key thing is the only vertices who lost colors from their list are the ones in A, but they also lost one out neighbor, so their out degree went down by 1, so the inequality still holds. Any questions about that? Okay. Okay, so basically I want to be able to apply that lemma to the line graph of a bipartite graph. So proof of Galvin's theorem. So let G be a bipartite graph. And let's just let K be the maximum degree of G, just so that, so I don't have to keep writing delta of G, I can just write K. I don't know if this is necessary or not, but we can assume that G is K regular because we had that trick we showed last time that if I have a bipartite graph, I can find it as a subgraph of a K regular bipartite graph. So we may as well assume G is K regular. Maybe it doesn't matter. Okay. And let's let H be the line graph of G. Okay. And yeah, we've got some kind of yeah, actually, the nice thing about this lemma is at this point, what I want to prove about H actually has nothing to do with any list assignment anymore. I don't need to consider a list assignment of lists. I don't care about list assignments. All I want to do is orient the edges of H to get a digraph that's kernel perfect and where all of the out degrees are at most K minus 1. Right? Because this lemma will take care of everything to do with the list, like the list coloring. So as long as I can make an orientation D of H that's kernel perfect, and if I can get these out degrees at most K minus 1, then I win. Okay, so our goal is to find a kernel perfect orientation like D of H with all of the out degrees, most k minus 1 for all vertices of H. Okay, because then we can just apply the lemma and we're happy. Okay. So yeah, I guess we need to remember H is the line graph. We're sometimes going to go back to G, look at G, and then look at H, and like kind of go back and forth a little bit. Okay. So as a first step, let me do something that is really not clear why it's useful, but we're going to see that it turns out it is useful. So I'm going to start by just applying this Koenig's edge coloring theorem. And just say, okay, well, if I if there aren't any lists, like I can color the edges properly with K colors. So I guess by, the Koenig edge coloring theorem, we can color, so we can, I guess edge color G, like properly with K colors. Okay. Again, not clear at all why this would be a good idea. Why is this going to help? But now what I'm going to do, I'm going to actually tell you the kernel perfect orientation right now, and then we're going to have to prove that it is kernel perfect. So we orient the edges of H as follows. So, okay. It's annoying because vertices of H are edges of G. So for two, like what are two adjacent vertices of H? They correspond to two edges of G that have an endpoint either on the left side of the bipartite graph or the right side. Like they share an endpoint on one side or the other. So, okay, so let's say E1 and E2 be edges of G corresponding to adjacent vertices of H. Okay, which all that means is that these are edges that have an endpoint in common, right? So I need to tell you how to orient, like should I orient the edge from E1 to E2 or E2 to E1 is what I need to describe. So so I've got this like edge coloring here with K colors. So kind of without loss of generality, let's assume, so let's call this coloring F. So without loss of generality, I can assume that the color of the first edge is less than the color of the second edge. They can't be the same color because they correspond to adjacent vertices of H. So, and this is a proper coloring. So I'm thinking of the graph G as having like, you know, it's a bipartite graph with some vertices on the left and some on the right. So if E1 and E2 intersect on a vertex on the left, so orient the edge E1, E2 of H from E1 to E2. Okay, so and then otherwise, we orient from E2 to E1. Okay, so this is like, yeah, this is how I define the orientation of H. So this defines like D, which is, yeah, this orientation that I wanted. I haven't proven it's kernel perfect, but this is that's the orientation. So yeah, for edges that share things on the left side, we orient from the edge of lower color to higher color. And if they share things on the right side, I orient from higher color to lower color. Okay. Okay. So it's actually, this out degree thing is pretty easy to prove. So suppose I've got an edge of the graph. I guess what is my out degree in D of the edge E? So I'm actually pretty sure this is exactly k minus 1. Because, okay, this edge E has some color. Let's say it has the color 5. Okay? Then on this side, so yeah, let's say f of E is 5. Yeah, on the right side, this edge E will have out neighbors, which are all of the edges incident to that vertex of lower color. So like the edge of color 4, 3, 2, and 1. Because, okay, this graph is k regular, so every vertex has an edge of every color incident to it. So yeah, on that side, this edge E will have these kind of, when I say on that side, I mean like in the graph H, there's no sides, but I guess I'm saying the edge E will have 4 different out neighbors corresponding to things that share a right endpoint. And then it'll have like, you know, for color 6, 7, up to K, it'll have an out neighbor for all of those colors coming from the left side. So basically it has an out, this edge E will have an out neighbor for every color other than its own color. So it's going to have exactly k minus 1 out neighbors. So this is like for all edges, for all vertices of H, or in other words, for all edges of G. I mean, these things mean the same thing. The vertices of H are the edges of G. So yeah, again, whatever color E has, for any edge of a lower color incident to the right endpoint, those will all correspond to out neighbors of that edge. And any edge of a higher color incident to the left vertex will correspond to an out neighbor. So yeah, it'll have k minus 1 out neighbors. Okay, so so this actually does half of this job for us, right? So the out degrees are okay. So I just need to prove it's kernel perfect. Any questions about this? Yeah, if you kind of think about this more, I mean, I just picked a number 5 here, but yeah, whatever color, if the edges of lower color coming from the right side will be out neighbors, and the higher colors coming from the left side. And then, yeah, it's going to be exactly k minus 1 out neighbors. Okay. So I want to show it's kernel perfect. This is kind of the hard part, right? I need to pick any subset of the vertices of D, every subset, right? And show that they all have kernels. But again, I can think of things back in the graph G or in H or in D or whatever, like a subset of the vertices of D or the vertices of H, same thing. Like a subset of the vertices of H is just a set of edges of G, right? I mean, H is the line graph, so a subset of the vertices of H is a subset of the edges of G, okay? So basically a subset of the vertices of H corresponds to like a subgraph of G, a spanning subgraph. Okay, so let S be a subset of the vertices of H. So I want to prove that H is kernel perfect. So I want to find a kernel in S. Or sorry, I want to prove D is kernel perfect. Like, yeah, I mean, it's a subset of the vertices of D, but these are the same thing, right? D is just an orientation of H. So let G prime be the subgraph of G with edge set S. Okay, because yeah, vertices of H are edges of G, so it's like I've basically taken a subset of the edges of G, right? Okay. So right, so yeah, we've got G prime, it has some edges. Here's what I'm going to do. I'm going to think of the vertices on the left side as being interns. This is coming back to something we've done before. And think of these ones as companies. Okay. And then, so I'm going to turn this into a stable matching problem. Now, okay, so the interns, So if I want to make this a stable matching problem, remember the setup is like we have interns and companies. Each intern has like an ordering on the companies based on like which ones they prefer the most to the least, and vice versa. So I need to tell you like an ordering. So each intern, so I get to pick the ordering, right? So, and then we're going to see what the solution gives us. So each intern orders companies that it is adjacent to in G prime. So remember, G prime is not actually the graph G. G prime has like has edges from S. So yeah, it doesn't have all of the edges of G. But anyway, so each intern orders the companies that it's adjacent to in G prime in order, well, in such a way that they prefer companies that they are adjacent to via edges of higher color. So remember, we have this coloring, this underlying coloring of G, of the edges of G, this coloring F. And so basically, like, an intern looks at the things it's adjacent to in G prime, and it says, I like the ones where the edges have higher color, and I put those at the top, and lower color gets lower ranking. So it prefers companies it is adjacent to via edges of higher color under F. So So yeah, if this intern has this edge, which has a color of 6, and then 3, and then 4, it'll put this company first on its list, then this one second, that one third. Now, when we did the stable marriage theorem, every intern had to rank every company. So we're going to do that still. I'm just going to say if it's not adjacent to some company, it puts them somewhere at the bottom of the list, and it just orders those ones arbitrarily. So, if intern I is not adjacent to company C, put them at the bottom of the list somewhere, like, and I don't really care how those are ordered. Yeah. Okay, so it puts the things it's adjacent to at the top of its list in order of decreasing color, and then everything else goes to the bottom. And then the companies do the opposite. So companies order the interns they're adjacent to by, so that the lowest color comes first. Okay, and again, any intern that company is not adjacent to just goes to the bottom. So non-adjacent, again, go to the bottom. Of the ranking. Okay. Is it clear what I'm saying here? They somehow, okay. So like we get to pick this ordering, and now the stable marriage theorem, or the stable matching or marriage or whatever theorem, tells you that there's a stable perfect matching. Now, I'm going to make it a perfect matching like in the complete bipartite graph. but like some of those edges will not actually be in G prime, but I don't really care. So all the edges that are not in G prime, I sort of just kind of ignore them. So anyway, so by the stable matching theorem, there exists a stable, well, yeah, kind of perfect matching okay, and then let M be the edges of that perfect matching that are actually in the set S. Okay. Not sure if that makes sense or not, but okay. Well, actually, you know, I'm calling this thing M for matching. I should probably call it K because that's going to be the kernel. So, like, because this, so first of all, this this matching in G prime, that's a stable set in D, right? Because remember, like H is like the line graph of G. So like two edges are not adjacent if they make, like a set of edges make a stable set in H if and only if they make a matching in G. Stable sets in G, sorry, matchings in G are stable sets of H. So my claim is that M is a kernel in the subdigraph of D induced by S. So first of all, it is a stable set because it's a matching in G. Okay, so that's good. So now I need to show that it has this other property that every vertex not in M, so or another, yeah, has an out neighbor into M. So let's say xy be, so yeah, vertices of D that are not in M are edges of G that are not in M. So let xy be an edge of G that it's not in the matching. So I need to show, so let's say, okay, maybe I'll call this edge E, but it's also xy. I mean, so I want to show that E to have an out neighbor in M. Okay, here's the thing. This edge, so, oh, sorry, this should be E prime, yeah. Yeah, so it's an element of S that's not an M. Okay, so think of X as an intern, Y as a company. So if there's a company that X prefers over Y, and if there's an intern that Y prefers over X, then it would not be stable. So because it's stable matching, no, sorry, what am I trying to say? Yeah, okay. It can't, So this is an edge that's not in the matching. So we can't have like, so either, like it can't be the case that X prefers Y over the thing it's matched to and Y prefers X over the thing it's matched to, because then these two would run away together and, so it would be unstable. So either X prefers the vertex it's matched to over Y, or Y prefers the vertex it's matched to over X. Okay. In either case, we end up with the edge XY having an out neighbor in M. Why? Because so in the first case, suppose that XY prime is in the matching. So this, let's say I break this into two cases. And Y, X prefers Y prime over Y. That means that the color of the edge XY prime must be higher than the edge XY, right? So since X prefers Y prime, we get that f of XY is less than f of XY prime. But then that's exactly the condition for this edge to have an arc to that edge. So XY, in the digraph D, there's an arc from XY to XY prime, because that is the condition for which they share an endpoint on the left, they share an intern or whatever, and yeah, that color is higher, so there's an arc. And the other case is similar. Okay, so it's a kernel. So that completes the proof. Okay, it's a little bit tricky kind of thinking back and forth between the graph and the line graph, but other than that, I think it's not too bad. I think that's kind of a surprising application of this stable marriage thing, which is kind of cool. Okay, so you guys ever heard of the concept of proof from the book? Erdős had this concept of well, there's this magical book up in, maybe not, I don't know, I don't think he was a very religious person, but sort of up in heaven or something, there's this book of all the best proofs of all the theorems, right? And okay, it's great to find the proof of a proof of a theorem, but you really want to find the proof that's in the book, right? You want to find the best proof. And this is considered probably the proof from the book of this theorem. And there's actually a book called Proofs from the Book, and this theorem is in that book. Anyway. Okay, maybe I'll give you another proof from the book, also about list coloring. This one's this proof is a little bit less connected to stuff in this course, so maybe don't worry about it. I don't think it's going to show up on assignments or exams or anything, but I'll just sort of quickly explain it to you. So this is Thomason's theorem. Which says that if G is planar, then the list chromatic number of G is at most 5. Which is kind of interesting because, right, we know that so it's very hard to prove the 4-color theorem, but planar graphs have chromatic number at most 4. Unfortunately, like the list chromatic number isn't at most 4. So you can find planar graphs and you can find lists that you can assign to their vertices such that they cannot be colored if the lists are of size 4, right? But if you've got 5 colors, you can. You might have seen also, like in a graph theory course, have you seen like that planar graphs can be colored with 5 colors? Okay, but this is like a more general thing, right? It's a stronger theorem. And actually, the proof of this theorem somehow, I think, is kind of easier or shorter than the proof of that you can just color with 5 colors without lists, which is a kind of a crazy thing. So like the original proof of this, like in the publication, is I think 1 page plus like maybe a few references went on to the next page. It's like 1.1 pages or something. So I don't know if I'll be able to explain it that quickly, but yeah, it's a short one. So it's by induction. Okay. So here's something I can assume. I can assume G is a near triangulation. Okay, all I mean by this is that the outer face, so when you have a planar graph, right, there's like inner faces and outer faces. So all of the inner faces are triangles, which if it wasn't, right, if I had a face of size 4, I could just put another edge, and it just makes it harder to color. So it just means the outer face might not be a triangle, but all the inner faces are triangles. So all are triangles. But yeah, the outer face might be longer. Doesn't really matter. Okay. Okay, what I'm going to do is something, it's completely crazy. So every vertex is like has a list, right? I'm actually going to make it harder for myself. Everybody on the outside face is only going to have it's going to have fewer colors. So, so actually I'm going to assume, actually there's going to be 2 special vertices. So, are on the outer face. So let's say, so they're just arbitrary vertices on the outer face, such that each of them, okay, each of them should have, and they're adjacent to each other. So it really looks like this. They've really got an edge between them. All I'm going to say is they've got at least 1 color each. Okay, but that's not, okay, if they each list has size 1, if it's the same color, that's going to be bad, because if they're adjacent, if that one only has the color red and that has red, it's already screwed. So I also have a constraint that, so if the lists, well, let's just say, and the union of the 2 lists has size at least 2. Okay. So I'm going to say all other vertices V on the outer face have lists of size at least 3. And then everybody else has to have 5. So all other vertices, let's say U, have lists of size 5, at least. Okay. And I want to show even with these, like this weaker assumption, I can still color it. And this is kind of insane, right? Like, why would I make it harder for myself? Why would I make the list smaller? But actually, it's kind of a magical induction proof in the sense that the fact that I have fewer requirements on my outer face, it's actually going to be quite useful because then it's going to be easier to apply induction because when I imply, like if I reduce to a smaller graph, the requirements I have on the outer face are easier to satisfy. Like I can kill some colors from some lists and still I might have 3 colors left and then I'm happy, right? So somehow, yeah, so I want to prove that if these constraints are satisfied, then by induction I can always find a coloring. Does that make sense? Maybe not completely. But there's a couple of special cases to consider. Like, okay, maybe the graph could have like a cut vertex. So, you know, I don't think I've ever explained what this means, but the picture is like maybe there's some vertex that could disconnect the graph if I delete it. But this is not too bad. Like what I would do, okay, so I'm going to be a little bit wishy-washy here, but I mean, I would just basically split the graph in half. I have to be careful. One of these halves might have like x1 and x2. Pick the side that has them, color it, and then like, okay, that might force the color of that vertex, right? So I color one side from the list by induction, which then tells me the color of that vertex. But then when I go to color this side, as long as like my x1 and x2 were on this side, then I can assume I can make that my new x1 or something, and I can color this side, okay, by induction. Okay, so that's kind of okay. I guess maybe there's a case 0 where it's disconnected, but then I just do the components separately. That's also okay. Case 2, G has a chord. Maybe I won't, well, I mean, it's basically just an edge between non-consecutive vertices on the outer face. But, I mean, the picture is just like, you've got this outer face, and imagine there's some edge that goes all the way across it. But I, again, do the same thing. I kind of break it into 2 halves. Okay, this time I need to be maybe a little bit more careful. But again, I take the side that has x1 and x2, I think. Yeah. Okay, I mean, x1 could be that one. And like both sides might kind of have x1 on them or something. Anyway, if one side has both x1 and x2, I color that one first by induction. That then forces the color of these two, but then these become my new x1 and x2 when I color the other side. And so then I can do it by induction. Okay, so then case 3 is that this doesn't happen. Okay. Okay. So case 3 is there's no chord and there's no cut vertex. Okay, pick V to be a neighbor of x1 that's not x2. So, and then I'm going to look around at the neighbors of V. Okay. Now I know that there's no chord. So like, if I look at the neighbors of V, I've got one of them, like I've got x1 is one of the neighbors of V. I've got another one over here on the boundary cycle. And these ones are like genuine internal vertices because there's no edge that cuts all the way across. So it's not, this one's like not on the boundary over here. These ones are internal. Okay, I need to be careful here. I need to do this properly. So that guy's, V's got 3 colors available to it. X1 might only have 1. I'm going to pick 2 colors that are available for V. But like if this happens to only have 1 color, it like okay, I can assume that. I mean, just by deleting colors, right? I can assume this is exactly 1. And now I pick C1 and C2 to be 2 colors that are available for V, but not the color that X1 has. So I can assume this, right? Because it only makes it harder. So I could just throw away some colors. Okay, so here's my procedure. Delete V from the graph. So it's gone. My outer cycle just becomes like, now it follows along the neighbors of V. I've just got a different outer cycle. Delete C1 and C2 from the list of the neighbors of V. On the interior, but I mean, oh yeah, only on the interior, not this one. So this one can have C1 and C2. So I delete C1 and C2 from the list of V in the interior. So if I call this one W, let's say, so when I say that, I mean not W. W could still have those colors. Okay. So my inductive hypothesis holds, right? What we get, I've removed this vertex. All the vertices on the boundary will still have 3 colors in their lists, except for these 2, which might have only 1. It's the same thing as before, right? Because these lists drop to 3. This list didn't change because I didn't delete anything. These lists might have dropped to 3, so I can color it. So color by induction. But now I need to color V. Okay, why can I color V? It's going to work, but so I'm here. I've colored G minus V, right? And I just need to give V a color. So what color am I going to give it? We can go as soon as we figure it out. Yeah? Exactly, yeah. Right, because these guys are not going to get C1 or C2. That's not in the list. This one's not going to get C1 or C2. I chose it to not be in the list of X1. It might be W, but yeah, just give it the other one. So yeah, so give V the color. So either of the colors, C1 or C2, that's not used on W. Okay, so that does it. So yeah, somehow there's some magic thing about like you could see this would not have worked if I had every vertex had list of size 5, right? I delete the vertex and delete some colors, and now it doesn't satisfy the hypothesis. You're screwed, right? So some magic thing about this induction. Okay, any questions about this stuff? Okay, then yeah, see you guys next week.